We already looked at the most basic model, a model that has only one component and produces Hello World. Now, let's take a look at a model with more than one component. This model represents a basic car wash. Keep in mind this is just a representation of a car wash and is not intended to simulate all aspects of a car wash in your neighborhood. Before we dive into the code, let's take a look at our situation in more detail. Our first component is the car generator. The car generator generates small cars and large cars. These cars go to the car wash to be cleaned. The car generator component has a port to connect to the second component. Our second component is the car wash itself. The car wash includes two wash bays, a large wash bay and a small wash bay. The large wash bay can wash large and small cars, while the small wash bay can only wash small cars. The car generator generates cars and sends them to the car wash via an event. The event is sent across the link. The car wash receives the event and places the car into the queue. If the large bay is busy washing a large car and a large car is next in the queue, the large car waits until the large bay is available. The small bay sits empty. Now that we have a basic understanding of what we are modeling, let's look at the code. We'll look at the project driver file first. The first component you see is setting up the car wash where we simulate washing the cars. There are 4 parameters in the component. The first is the number of hours to simulate. The second is how long each clock tick should simulate. So this configuration is going to simulate 24 hours, and each clock tick will represent 1 minute. The next 2 parameters determine how long it takes to wash each type of car. The number represents the number of clock ticks it takes to wash a vehicle. Since ours is 1 tick every 60 seconds, this is the number of minutes it takes to wash a car. The second component helps simulate cars going to the car wash. The car generator sends car events to the car wash: a small car, a large car, or no car at all. There are 2 parameters in this component. The first is delay. The delay is the time between car events. The second is a random seed. This determines what cars will arrive. Changing this value changes the pattern of small, large, and no car arrivals. Note the tick frequency and delay are both 60 seconds. For best results, the tick frequency in the car wash component should be the same as the delay in the car generator component, though you can change them to see what happens if cars come more or less often. The last line sets up the connection between the 2 components. We see that the car wash component is set to connect via its port to the car generator component at a speed of 1 picosecond. Generally, links are the same speed in each direction, as they are in this example. However, SST does allow links to be different speeds in each direction. Now that we've walked through the organization and makeup of the project driver file, let's look at the car generator in more detail. The car generator header file defines what a car generator looks like and registers info about the component with SST, as well as the constructor and destructor for the car generator, and the setup and finish, which are required by SST. We also have a handler for the clock tick event. On each tick of the clock, we send a car event to the car wash. As we scroll down, SST ELI register component registers the component information with SST. Underneath, we have the class we're registering. Notice there are no quotes, so it's just the class. Below that, we have the element library name, Simple Car Wash, and the component we are registering, Car Generator. We also have a version number, a description, and a category for the component. This should look somewhat familiar to what we saw in the Hello World example. Moving down the screen, SST ELI document params registers the parameters that our component uses. The delay param will change the rate at which car events are sent. And we also have a random seed that affects the pattern of cars generated for the car wash. Both include a description, and the delay has a user-specified example value of 60 seconds. The default value is in the C++ file. We'll review that in a moment. Continuing on, SST ELI document ports registers the ports. This component only has one port used to transmit car events. Internally, we see the component is using SST's string event to send cars to the car wash. At the bottom are some private variables that we'll be using within the component. Now, if we go to the car generator C++ file, we'll see how all of this is implemented. Here we get the parameters from our project driver file. Each parameter has a default value defined here. The delay's default is 60 seconds, and the random seed is 15, 15, 15. Ideally, this would match the values we just saw in the previous file, the car generator header file. These values can be overridden in our project driver file. This is where we set up a clock for how fast the project driver file specifies. Also, we are specifying a handler function that is called every clock tick. We'll look at this in more detail in a minute. This area creates the random number generator with the random seed. Continuing down the screen, here is where we are configuring our port that's used to send the car events. We only have one port in this simple model. If it's not set up in the project driver file, we will fail with an error message. And here we have the setup and finish functions. As we continue down, we see the clock handler. With every tick of the clock, we generate a random number. We use mod 3 to ensure every random number is a 0, 1, or 2. 0 for no car, 1 for a small car, and 2 for a large car. And then we send it out of our port, down the link, and to the simple car wash. Now, let's look at the simple car wash header file. This is where we register our component, port, and parameters with SST. Here we can see the constants of the model. For our model, a 0 means the wash bay is empty, and a 1 means it's full. As we scroll down, we have the constructor and destructor, the setup and finish, the clock, and the event handler. This handler is called every time a new car arrives. A little further down, the items listed here keep track of how many cars arrived, how many cars were washed, if a bay is occupied, etc. Similar to what we saw with the car generator, this section registers the car wash, including the component, library, a description of the element, and the component category. Here are the parameters: the clock frequency, the clock count, how long to run the simulation, and how long it takes to wash a large or small car. Within the ports, the interface has to be the same as the interface in the component where the cars are coming from, in this case, the car generator. As we scroll down, we have a number of variables and functions to run the simulation. We also have a few statistics that we'll keep track of when we run the simulation. A little further down, the car wash clock tick function checks for a new car in the queue that's waiting to be washed, and then removes the car from the queue once the car is sent into the wash bay. We're also tracking whether the wash bay is ready. Now, let's switch over and look at the C++ file. Here's where we get the parameters from the project driver file, such as how long we're going to run the simulation, clock speed, and wash times for small and large cars, as well as calculating how many clock ticks are in an hour, so we know when we have run the simulation for the specified number of hours. And then we're registering this as a primary component and telling SST not to end the simulation until the component actually says to end the simulation. We register the clock. At each tick of the clock, either we continue washing the cars in the bays, or we send in a new car from the queue once a bay is empty. We configure our port, which is very similar to what we saw with the car generator, except here we have a handler. Here we are initializing some variables. These variables will keep track of how many small and large cars arrived, and how many small and large cars were washed. The handler will handle the car events as they come into the car wash. Let's look at the handler in more detail. Every time the handler sees an event, we're checking to see that it's valid. We change the string into an integer that determines our car type and adds the car to the queue, as well as keeping track of some statistics. Remember, we have 3 car types: small car, large car, or no car. The cars are placed into a queue so that, just like in the real world, we take the cars in the order they arrived. On each tick of the clock, we first check to see if we should output hourly statistics. This component produces an hourly report so you can see how many small cars arrived, how many large cars arrived, and how many times no car arrived. Then, we check to see if the simulation time has elapsed, and if it has, the simulation is complete. The car wash clock tick function is where the component checks if there are any empty bays, and if so, it will take a car from the queue and put it in the bay. If we scroll back up, we see that the component is configured such that when the simulation is complete, the component produces a summary report. The report tells how many cars were washed and how many cars are still in the queue. So let's see this model in action. To run the simulation, we'll run the SST tests simple car wash py command in the terminal. And here are our results. We see that we washed 527 cars. 265 of them were small cars, and 262 of them were large cars. Now, it's your turn. If you didn't download SST earlier, return to the Get SST section before continuing. If you're unsure what to change, here are a few ideas. The time it takes to wash a small car, a large car, or both. How many hours we are simulating. Currently, that value is set to 24 hours. Once you make a change, run the simulation and check out the results. How many cars were washed? Did the number increase? Did it decrease? Pause the video now to explore SST. We already looked at the most basic model, a model that only has one component and produces Hello World. We also looked at a model with 2 components, where one was a car generator and one was a car wash. Before we look at our third model, let's set the stage. The car wash owner met with his investor. The investor is pleased with how the car wash is doing overall, but is looking to increase revenue and profit. The investor has decided to invest a large sum of money into the car wash, but in return, expects to see a return on his investment. The car wash owner now needs to decide how best to invest this money. He's decided to use a model to simulate a few options. Options might include buying new equipment that washes cars faster, adding a new bay. Or perhaps both. So let's take a look at the code. With this model, we have the ability to add subcomponents for each type of wash bay versus the previous model that had everything hard-coded. For the car wash component, we still have a tick frequency and simulation time, but the wash times for small and large cars are handled by the bay subcomponents. Now we have a few subcomponents. These are the bays that wash the cars. Each bay has 3 parameters: the size, 1 for small cars and 2 for large cars, small car wash time, and large car wash time. Note that the large car wash time is only used if the bay is able to wash large cars. And we have the car generator. This model also has SST statistics. SST statistics provide a standard way to collect data. That data is presented in a format that can be further processed by other statistical tools. You can enable or disable SST statistics globally at the component level or individually within a project driver file. The link between the car wash and car generator is also the same. When we look at the cargenerator.h file, we see that the code remains the same. Taking a look at the generator C++ file, again the code remains the same. We still generate a random number and generate a simulated car to send to the car wash component. Next is the bay. This is a new class that was added for this model. A bay looks a lot like the components we've seen before. It has a constructor and destructor. It also has functions such as new car to identify when a new car arrives, bay size, whether the bay is occupied or not, and the tick function is run for every tick of the clock by the parent component. And then we have the registration of the subcomponent, where we have the class, the library, a name, the version, and a description. The last line indicates it is a subcomponent of the car wash. The parameters that the bay has are size, 1 for small, 2 for large, small car wash time, and large car wash time. SST statistics for tracking the number of cars washed, and how long the bay is idle. As we scroll down, we see variables for output to the screen such as size of the bay, whether it's occupied or not, and how long we have left before the car in the bay is washed. Now, let's look at the C++ file. The constructor should look familiar to you by now. Here we have the bay size, which indicates whether the bay can accommodate a small or large car. We also read the wash times for small and large cars. Here, we register statistics for the bay. And then here, we indicate whether the bay is empty or occupied. We'll start off with an empty bay. Scrolling down, this function accepts a new car. If the bay is empty, it checks to see if it's a large car for a large bay, and then it determines how long the bay should be occupied, based on the time the subcomponent states that it takes to wash that type of car. The subcomponent is set to return false if the bay is full, or we try to place a large car in a small bay. Moving down, here we return the size of the bay, whether it's occupied or empty. And this tick function decrements the time the bay is occupied when there is a car in the bay. If the time is 0 or less than 0, the bay empties. Moving over to the car wash itself, we don't see a lot of changes. The header file is very similar to the simple car wash version, except now there is a prototype for a subcomponent and SST statistics. At the top of the file is the prototype for the bay. Scrolling down, we register the subcomponent slots. Finally, we add a variable to store a list of our subcomponents. Moving over to the C++ file, the simulation time and the tick frequency, and the setting up of the subcomponents. Note that there must be at least one bay. Then here we create all of the subcomponents. As we continue down, we register the clock for the simulation. Here, we register the statistics for the number of cars that were washed, as well as the number of cars waiting. If we scroll a bit further, we see the setup function that sets the initial values for the wash time, the number of cars that arrived, etc. Below is the finish function that prints out the final report to the screen after we run the simulation. The handler adds cars to the queue and keeps track of the number of cars that arrived and how many cars are waiting to be washed. The only difference between this and the simple car wash is this model uses SST statistics. Let's check out the clock handler. This is similar to what we saw before for the car wash clock tick function, except now, car wash clock tick runs over subcomponents rather than hard-coded with two bays. Scrolling down, note that the QA car function is the same as we saw in the simple car wash. In the car wash clock tick function, the first step is for the simulation to go through all of the subcomponents and run the tick function, so if the bays were full, it will decrement the time that the bays are occupied. At the same time, we're also counting how many bays are empty. The simulation will loop through all of the subcomponents and try to fit cars into a bay, as well as use SST statistics to track cars waiting and cars washed. Cars continue to enter the car wash, but eventually we'll loop through all of the subcomponents and find that all of the bays are full. Or there will be a large car with only a small bay open, so the large car remains in the queue and waits. Or if all of the bays are full, the next car in the queue waits. If we run the simulation, our results are formatted similarly to what we saw before, and we can see that we were able to wash 527 cars. In this model, having the bays be subcomponents rather than hard-coded makes it very easy to add a bay. We simply copy over these lines of code, add it in below, and increment the slot number by 1 each time. Change the name of the subcomponent variable. Now, when we run the simulation again, we were able to wash 945 cars, thanks to the addition of a large bay. Now it's your turn. If you didn't download SST earlier, return to the Get SST section before continuing. Try decreasing the delay in the car generator so that cars arrive at the car wash faster, and then check out your results. How many cars were washed? Did the number of cars increase? Try changing the time it takes to wash a small car or a large car. Or consider changing the tick frequency of the car wash to 1 second, and try simulating wash times such as 1 minute 30 seconds for a small car.